exercise for the case of cylinder, means we would be finding out the temperature distribution, and then we would be finding out the thermal conductive resistance in cylindrical coordinate system. See, if you recall, we had started with the Cartesian coordinate system heat diffusion equation. So over here we will do the same thing, means we will start with the heat diffusion equation for cylindrical coordinate system. So starting with the heat diffusion equation for cylindrical coordinate system, and then imposing the same four conditions, means we will say that the heat transfer is one dimensional. So over here we would be taking the radial direction heat transfer, because as explained earlier, most of the times heat comes out or goes in or comes out outwardly, radially. So therefore we would say that temperature is a function of R, means at different radii values or at different radial locations temperature would have different values, and therefore heat would be going outside of the pipe in a radial direction. And we will say that temperature does not vary circumferentially or along the axis of the pipe, and we will say that there is no, so therefore the second and the third terms will vanish, and we will say that there is no internal heat generation, so therefore Q dot will also get cancelled out. And if the system is working under steady state conditions, so therefore T by T would be 0. So for these conditions, for these four conditions, the same four conditions that we had in the case of plane wall, the above equation would reduce to the first term only, 1 over R dava by dava R of Kr dava T by dava R is equal to 0, and then we can replace dava with a D for the very obvious reason that we have discussed several times before. Now if K is constant, the thermal conductivity is constant, means if we say that the material is isotropic, so therefore K would come out of the differential sign, and we would have R dt by dr within the differential sign. So 0 multiplied by R would become 0, and 0 divided by this constant K would also become 0. So we will be left with d by dr times R dt by dr as equal to 0. So over there in the case of plane wall we had integrated this thing twice, so over here we will do the same thing, we will integrate it twice. So integrating it for the first time will make the d by dr sign vanish if we integrate with respect to R. So we will be left with R dt by dr equal to the integral of 0 would be constant. So R dt by dr would be equal to C1, therefore dt by dr would be C1 over R. And integrating it the second time, integral of dt by dr with respect to R would be T, just like integral of dy by dx with respect to x would be y. And on the right hand side it is 1 over x, so integral of 1 over x is log x, because differential of log x is 1 over x. So on the right hand side we would have C1 log of R as the integral of C1 over R, and we would have C2 plus C2. So again we are having the same situation as we had in the case of plane wall. You can see that there are two unknowns C1 and C2, and we have to find out those two unknowns C1 and C2, for which we need two boundary conditions, just like we require two boundary conditions over there in the case of plane wall. And if you recall, what were those boundary conditions in the case of plane wall? Those were two very simple boundary conditions. All we said was that we knew temperatures at two locations, and the same boundary conditions will be taken over here in the case of cylinder. We will say that we know temperatures at two locations, at two radii. So we will say that we know temperature at inner radius and we know temperature at outer radius, or R1 and R2. So this is the equation that we have come up with, and boundary conditions are that at R is equal to R1 or at R is equal to Ri, T is equal to T1 or T is equal to Ti. And the second boundary condition is that we know that at R is equal to R2 or R2 may be written as R0, the temperature has the value of T2 or T0. So this is these are the two boundary conditions that are that have been shown over here, that at inner radius temperature is T1 and at outer radius temperature is T2. Means we know temperatures at the two radii, inner radius and outer radius. Now if we apply the first boundary condition in equation 1, we will do the same thing. We will apply both of those boundary conditions in equation 1 to get the values of C1 and C2, and once we find out C1 and C2, we will put them back in 1 to get temperature as a function of R. And that is the same thing that we did in the case of plane wall. So procedure for finding for carrying the things out is the same. So if we now put the first boundary condition in equation 1, we get that T1, because the first boundary condition says that where R is R1, T is T1. So in place of R we will write R1 and in place of T we will write T1. So this is what we will get. And when applying the second boundary condition in the same equation, the second boundary condition says that where R is R2, temperature has a value of T2. So in place of R we will write R2 and in place of T we will write T2. So this is what we will get. Now you can figure out straight away that if we subtract equation 3 from 2, we would be able to get rid of C2. So therefore we would be able to find out the value of C1. So if we subtract the two equations, for example if we subtract 3 from 2, we get on the left hand side as T1 minus T2, and on the right hand side C2 will get cancelled out and we will be left with C1 times log of R1 minus log of R2. Therefore C1 would be T1 minus T2. Therefore C1 would be T1 minus T2 over log of R1 minus R2, and this log of R1 minus log of R2 can then be written as log of R1 over R2. This can then be written as log of R1 over R2 because log A minus log of B is log of A upon B. This is the value of C1. See, we only have the known quantities, means R1, R2, T1 and T2, and we do not have any T or any R. Now if we put this value of C1 in either 2 or 3, the result would not matter, the result would be the same. Let's say if we put it in 2 to find out the value of C2, so it says 2 says equation 2 says T1, so T1 is there, is equal to C1 log of R1. So we will write the value of C1 which is T1 minus T2 over log of R1 over R2, and it is being multiplied by log of R1, so we will multiply it by log of R1 and then plus C2, so plus C2 is there. Therefore C2 would be T1 minus this whole term, it would be T1 minus this whole term. Now we have found out C2 and C1, therefore we will put both these, one of them is coefficient and one of them is a constant. We will put both these in equation 1 to get temperature as a function of R. Over there in the case of plane wall we had found out temperature as a function of X, but over here since it is cylindrical coordinate system, so therefore we would be finding out temperature as a function of R, radius. So if we put both values of C1 and C2 in equation 1 says that T is equal to C1 times log R. So this is C1 which is being multiplied by log R and then plus C2. Therefore this whole thing is C2. Now if you see, we have T1 which can be written separately, and these two terms means these two terms have got a lot in common. these two terms have got T1 minus T2 over log of R1 over R2 common. So if we take this thing as common out of these two terms, so we will be left with log of R minus log of R1. So we will be left with log of R minus log of R1. So therefore T is T1. Let's go on to the next page. Is this thing log of R minus log of R1, and this log A minus log B can then be written as log of A over B, log of R over R1. So from here to here I have not done anything, but I have only written this term first and then T1 after. So just to give it, just to write it in the form of mx plus c. It is not really mx plus c, but in fact the R has been written first and then the constant quantity has been written later. Now you can see that over here this T is a function of R because T1 is constant, T2 is constant, R1 is constant, R2 is constant, R1 is also constant, and T1 is constant as well. So therefore T varies with R only, with log of R only. Over there in the case of plane wall, T was varying linearly with X. Over here temperature is varying logarithmically with radius. So after finding that out, what did we do over there in the case of plane wall? We had started with Fourier's law of heat conduction. We will do the same thing again. We will say that Q in radial direction is minus Ka dt over dr, and this dt over dr means we need to differentiate temperature with respect to R. And in order to differentiate temperature with respect to R, what we need is a function of temperature in terms of R. And where is temperature in terms of R? This is temperature in terms of R. So it says that dt by dr of T. So we will write d by dr of T, and in place of T we will write this whole equation. And its differential is not that difficult at all. See, there are two terms. The first term, a very big term, and then the second term is a very small term. It is only T1. So if we are differentiating with respect to R, differential of T1 with respect to R would be 0 because there is no R in there. So all we need to do is differentiate this first term only. Now even in this first term, see where is R? This is the only place where we have R. And we do not have R anywhere else. So it is not the case of differential of U over V. See, it is a constant quantity. T1 is constant, T2 is constant, R1 is constant, R2 is constant. So all those are constant quantities, which is the coefficient of log of R. So that coefficient would be written as it appears, and then log of X will be differentiated. See, the differential of log X is 1 over X, and means 1 over whatever X is. Our X is right now R over R1, so it would be 1 over R over R1. And then R over R1 will also be differentiated with respect to R, because you can say that it is X over 5. So differential of X over 5 would be 1 over 5. Therefore differential of R over R1 with respect to R would be 1 over R1, because differential of R with respect to R would be 1. So this is what we will get. Now R1 will get cancelled out and R will also get cancelled out. See, this area has been written as 2 pi RL, because 2 pi RL is the circumferential area through which the heat would come out radially, would come out in radial direction. Therefore it would be 2 pi RL and not pi by 4 d square. So what are we left with now? Minus 2 pi KL, minus 2 pi KL, and this whole thing, T1 minus T2 over log of R1 over R2, T1 minus T2 over log of R1 over R2. Now if we take this negative sign over here, we will not write it as T2 minus T1. Why? Because if the heat is going out radially, it means that T1 is greater than T2. But what you will realize is that if you take a look at the denominator, R1 will always be less than R2 because R1 is inner radius and R2 is outer radius. So this ratio would be a quantity less than 1, and the log of a quantity less than 1 would be negative. So if we bring this negative sign in here, it will make the denominator positive all the time. So if we bring this negative sign in here, what is the denominator? Log of R1 minus log of R2. So if we bring this negative sign in here, it would become log of R2 minus log of R1. So log of R2 minus log of R1 can then be written as log of R2 over R1. And the rest of the things remain unchanged. 2 pi KL remains 2 pi KL, T1 minus T2 remains T1 minus T2. And what is this thing? It is QR. It is QR. Heat transfer in radial direction. If in the last step we now write it in the same form means in the form such that we keep delta T in the numerator and take the rest of the parameters or rest of the terms in the denominator, then we will write it in this form. T1 minus T2 will be there in the numerator, and log of R2 over R1 divided by 2 pi KL would come into the denominator. If we take this 2 pi KL in the numerator, we will get the same expression again. And then comparing it with V is equal to IR or I is equal to V over R. And we have done it several times in the past. In the case of plane wall, conduction across plane wall, in the case of convection, and in the case of radiation. And if we then compare it with V is equal to IR or I is equal to V over R, the analogy can be seen. The quantity that flows in the electrical circuits is current, and the quantity that flows in the thermal circuits is heat. Current flows as a result of potential difference. Heat would flow as a result of temperature difference. And whatever we have in the denominator is resistance. Therefore, whatever we have in the denominator over here would be thermal resistance. And it is conductive. Why? Because we are using Fourier's law of heat conduction. And since we are dealing with cylindrical coordinates, so log of R2 over R1 over 2 pi KL or log of outer radius over inner radius divided by 2 pi KL is the expression for conductive resistance in cylindrical coordinate system. This is the expression for conductive resistance to find out the conductive resistance offered by a cylindrical wall. Just like L over Ka or delta X over Ka was the conductive resistance offered by plane wall, the conductive resistance, thermal conductive resistance offered by a cylindrical wall would be log of outer radius over inner radius divided by 2 pi KL. Now let's take a combined thermal network in which we have conduction as well as convection taking place. So what is happening over here is that there is a hot fluid passing through the inside of the pipe. So it is a hollow pipe, and there is a certain wall thickness of the pipe. So inside the pipe there is a hot fluid such as, for example, steam at 500 degrees Celsius, and then we have a hot fluid outside the pipe such as air. So therefore the heat will flow outwardly in radial direction. So between the hot fluid, between the steam inside the pipe and the inner surface of the pipe, see, there is an R1 and then there is an R2. What is R1? R1 is the inner radius, means the inner surface radius, and R2 is the outer surface radius. So between the steam which is flowing inside the pipe, through the pipe, and the inner surface of the pipe, there would be convection, and associated with that convection there would be a convective resistance. And how do we express convective resistance? 1 over HA. So this is 1 over HA, where H is written as H1, because if there is a steam flowing it would have a different H, and if there is air flowing there would be a different H. So it is 1 over H1 times area. what is the area through which the convection heat transfer is taking place? It is the inner surface area, which is 2 pi RL, and at the inner surface R has a value of R1. R is equal to R1. So therefore 2 pi RL, where R would be written as R1. So the heat will reach from steam to the inner surface of the pipe, and then from the inner surface of the pipe it will flow, the heat will pass, the heat will flow through the thickness of the pipe. And what is the thickness of the pipe? It is R2 minus R1. So the pipe will offer conductive resistance. So over here R2 would be the conductive resistance in cylindrical coordinate system, which would be log of outer radius over inner radius, means log of R2 over R1 divided by 2 pi KL. This is what we just derived on the previous slide. So now the heat will reach, the convection is, the inside convection is taking place between T infinity 1, the steam is at, for example, T infinity 1, and the inner surface of the pipe is at T1 or TS1. Now the outer surface of the pipe is at a temperature of TS2. So therefore this conductive resistance would be between the nodes at which the temperatures would be TS1 and TS2, and between the outer surface of the pipe, which is at TS2, and the hot fluid, which is at T infinity 2, between TS2 and T infinity 2, there would be convection taking place. Associated with that convection, there would be a convective resistance, and the convective resistance is given as 1 over Ha, where H is H2, and area would be, what is the area through which convection is taking place? Again it is 2 pi RL. Again it is 2 pi RL, where R is equal to R2. So kindly note that in the case of plane wall, the area on both the sides were the same, but over here the area inside the pipe has a different value of 2 pi R1L, and the area on the outside surface of the pipe has got a different value, which is 2 pi R2L. So now we will do the same thing, means we will write Q in terms of delta T over resistance. So if we write it as T infinity 1 minus T infinity 2, so what are the resistance that fall in between T infinity 1 and T infinity 2? All three, R1, R2 and R3. So that in the denominator we will write R1 plus R2 plus R3. If we write Q as T infinity 1 minus T1, as T infinity 1 minus T1 or TS1, so between these two nodes we only have R1. Therefore in the denominator we will only write R1, resistance 1, or 1 over Ha. Now if we write this delta T as T infinity 1 minus TS2 or T2, so in between these two nodes we have got two resistances, R1 and R2. So in the denominator we will write R1 plus R2, means 1 over Ha plus log of outer radius over inner radius divided by 2 pi KL. So we can write this Q in several forms depending upon what temperature difference do we keep in the numerator, and associated resistances that fall in between those two temperatures that we have kept in the numerator. And all those Q's would be the same if the system is working under steady state conditions. Otherwise they won't be the same. Now this is another diagram for the same thing. Between T infinity 1 and T1 we have convective resistance, means 1 over Ha. Between the inner surface of the pipe and outer surface of the pipe there would be the thermal resistance in cylindrical coordinate system, means log of R0 over Ri divided by 2 pi KL. And between the outer surface of the pipe and the outer air there would again be convection, associated with which there would be a convective resistance, which will be given as 1 over Ha, where H would be equal to H2 and area would be equal to 2 pi RL, where R would be equal to outer radius R2. Right? Total resistance would be the sum of the resistances, would be the simple sum of the resistances. Why? Because all those three resistances are connected in series. So whenever the resistances are connected in series, the equivalent resistance is the simple algebraic sum of those resistances, which will not be the case if the resistances are connected in parallel. Now let's take a composite cylinder. Composite cylinder means a cylinder composed of more than one materials. So there are three materials. A composite cylinder is very easy to understand. If we have a steel pipe wrapped in insulation, so if we have a steel pipe wrapped in insulation, there are two materials. One is the steel itself and the other one is the insulation. Over here, this composite cylinder consists of three materials, A, B and C. So A would have a thermal conductivity of Ka, B would have a thermal conductivity of Kb and C would have a thermal conductivity of Kc. And suppose that inside there is steam at a temperature of T infinity 1 and the convective coefficient between the steam and the inner surface of the pipe is H1. Similarly, on the outside it may be air, and air would be at a temperature of T infinity 4. Again, they could have written T infinity 2 after T infinity 1, but they chose T infinity 4, that's fine. And between the outer surface of the cylinder, which is at TS4, see, the inner surface of the pipe is at TS1, and then at the interface of A and B the temperature is T2, and at the interface between B and C the temperature is T3, and at the end of material C, means at the outer surface of the cylinder, the temperature is TS4. So between TS4 and the outer air, which is at T infinity 4, there would be convection, and the convection coefficient between the two is given as H4. Now this would be the, since there are three, it is a three-layered wall, it is a three-layered cylinder, so there would be three conductive resistances. There would be three conductive resistances, 1, 2 and 3. And how do we write the conductive resistance in cylindrical coordinates? It is all the time log of outer radius over inner radius divided by 2 pi kl. Now for A, what is the outer radius? R2, and what is the inner radius? R1. So it is log of R2 over R1 divided by 2 pi kl, where conductivity is the conductivity of A and L is the length of the cylinder. Now in case of B, what is the outer radius? Outer radius is R3, and what is the inner radius? Inner radius is R2. So log of outer radius over inner radius would be log of R3 over R2. Would be log of R3 over R2 divided by 2 pi kl, where K would be the conductivity of B. Similarly, in case of material C, it would be log of outer radius over inner radius. Now what is outer radius in case of C? It is R4. And what is the inner radius of C? It is R3. So it would be log of R4 over R3 divided by 2 pi kl, where conductivity would be the conductivity of material C. And we would have TS1, T2, T3 and T4 or TS4 at the nodes. Over here we have got T infinity 1. So between T infinity 1 and the inner surface, which is at TS1 or T1, there would be convection, associated with which there would be convective resistance. And how do we express convective resistance? 1 over HA. H is H1, and what is area? Area would be 2 pi RL, where R would be R1. Similarly, on the outer side, it would be convection between TS4 and T infinity 4. And convective resistance is given as 1 over HA, and area would be 2 pi RL, where R would be equal to R4. So this is how all the resistances would be written. And then you can write Q in various forms. I have only written one form, but Q can be written in various forms depending upon the temperature difference in the numerator. So if we write T infinity 1 minus T infinity 2, so in between T infinity 1 minus T infinity 2 or T infinity 4 rather, kindly correct it as T infinity 4. how many resistances are there? There are 1, 2, 3, 4, 5 resistances. So all those 5 resistances would come into the denominator. You may write it as T infinity 2 or T infinity 4. Now this is another view. In fact, as I explained in one of the previous lectures, that those pinkish figures are taken from Yunus Singhal and those orangish figures are taken from Incorporated Dewitt. Again, that is the same thing. It is a 3 layered wall and there are 3 materials having conductivities of K1, K2 and K3, and there is convection inside and convection outside. Now the last thing that I would leave upon you, I have derived the temperature distribution and therefore the conductive resistance for plane wall and for cylindrical coordinates. I would leave the spherical one on you. All you need to do is follow exactly the same procedure and you will reach to this result. What is the result? QR. In case of a sphere, you will get this expression, and upon its comparison with V is equal to IR or I is equal to V over R, we will say that the quantity that flows in electrical circuits is the current, whereas the quantity that flows in thermal circuits is heat. Current flows as a result of potential difference and therefore the heat flows as a result of temperature difference, and whatever is left in the denominator is resistance. So therefore whatever we have over here in the denominator is the resistance. 1 over 4 pi k times 1 over Ri minus 1 over R0 or 1 over R1 minus 1 over R2. This is the conductive resistance in spherical coordinate system. This is the conductive resistance in spherical coordinate systems. 1 over 4 pi k times 1 over Ri minus 1 over R0. Sometimes people get confused whether it was 1 over Ri or 1 over R0 first. See, Ri is greater than, sorry, Ri is less than R0. Inner radius will be less than outer radius. So Ri is less than R0. So therefore 1 over Ri would be greater than 1 over R0. So 1 over Ri would come before 1 over outer radius. This is one way just to keep the track that 1 over Ri would be written before 1 over R0. Before 1 over R0. So concluding this thing, we have got convective resistance as 1 over HA and radiative resistance as 1 over HRA, but the conductive resistance is different for plane wall, Cartesian coordinate system, cylindrical coordinate system and spherical coordinate system. In case of Cartesian coordinate system, the conductive resistance is L over Ka or delta X over Ka. In case of a cylindrical coordinate system, the conductive resistance is given as log of outer radius over inner radius divided by 2 pi kl. Whereas in case of a spherical coordinate system, the thermal conductive resistance is given as 1 over 4 pi k times 1 over Ri minus 1 over R0. This is the almost all about the thermal networks. We would be discussing a few things here and there, but this is almost all about the thermal networks. So you wouldn't have find it difficult at all. Rather, it's quite interesting. There are 1 or 2 smaller topics that we will discuss with time, and those are one is the contact resistance and the other one is the critical radius of insulation. We will come across those in later lectures.